So we're going to continue with sort of another type of integration, which is, in this case, we're going to learn how to do integrals of surfaces. So not just of volumes, but once we have a surface, let me draw some sort of surface. I guess I have surfaces right there that I could have used. But I have a surface, and I want to find a piece of that surface and then find the area of that surface. To be able to do that, we're going to need to learn how to parametrize surfaces, which is the same way we parameterize lines. We parameterize curves in space using one parameter. So for surfaces, it's going to be like the parameterization of a line, but with two parameters. And we're doing this so that we can finish on a strong note this class by stating Stokes' theorem and the divergence theorem, which are going to be generalizations, as I said before, of Green's theorem. But so in those generalizations, now we're going to, instead of doing an integral of area, Green's theorem was stated in 2 dimensions. They're going to be 3-dimensional versions of Green's theorem. So for that, we're going to do integrals over surfaces instead of integrals of areas in the plane. So first step first, we need to learn how to parameterize surfaces. So what we're going to do is, as I said, we're going to parameterize surfaces by using a parameterization very much like we did parameterizations of curves, like so. We parameterized surfaces or lines or curves like this. This would be just the x, y, and z coordinates. And here we are also going to have x, y, and z coordinates for our surface. But when we parameterized curves, which are one-dimensional objects, we only needed one parameter. When we're parameterizing surfaces, we have 2 different parameters. So what we're going to do is there's going to be some region where our parameter space is. And then for each one of these points in here, that corresponds to some point on a surface in 3D. And every point on this area, on this region of the surface, corresponds to some point in that parameter space. And then we're going to do things like we're going to look at lines here and then see what those lines look like over here. There are going to be some curved lines. And that's going to give us paths within the surface, which are parameterized like we parameterized curves in the past. So this line parameterizes some line over here. This line over here would parameterize some other line that passes through that point, etc. So how do we do this? Let's just see what these look like. So let's try to identify and sketch the surface with vector equation given by our uv is 1, u plus v. So what does that look like in space? Let's draw our space here, x, y, and z. And the characteristic here is that x is always 1. Okay? So this tells me that x is fixed equal to 1. Y is given by a parameter u, and z is given by u plus v. So both parameters come into play with z. And since x is equal to 1, every single point of this surface has to be in, well, this is x equals 1, but x equals 1 is the equation of a plane. That is the plane that has all the coordinates are 1. So let me draw it like so. Okay. That's the plane x equals 1. And now the other 2 coordinates are giving me some other properties. Now, because here, there's no restrictions on u and v. So what is happening is that we really have our parameter space is all of the R2, all of the plane. And then through this parameterization, we're going to parameterize something in 3D, but the parameters can be anywhere. And since the parameters can be anywhere, that means that u can be any real number. And that tells me that I can get all the possible y values. And here, u and v are any real numbers. But that tells me that just set u equal to 0, then as v runs over all the possible numbers, I actually get all the possible z values also. So I am actually parameterizing with this parameterization. I am parameterizing the entire plane x equals 1. Okay, so that is what it parameterizes. It parameterizes the plane x equals 1. This parameterizing in a weird way, a slightly weird way. It's not. It would. If I was asked parameterize the plane x equals 1, I would have parameterized this at 1, u, v, because then u corresponds to the x coordinate, v corresponds to the z coordinate, right? It is parameterized in a slightly awkward way, in the same way that when we parameterize lines, sometimes we parameterize a line with different speeds or in different ways, because we have a line, but then there is some motion within the line that we want to express. And in here, it's parameterizing the plane for whatever reason. Sometimes the parameterizations are not the most obvious ones. Any questions about this sketch? All right. Let's try a different one. So what happens with this one? This is u plus v. So again, there is no restrictions on the u and the v. So the parameter space is all of R2. And then I'm going to something in 3D that I want to try to sketch. I'm going to do a bigger axis here. Any ideas, any suggestions of how to sketch this thing? What are we looking at? If you go back a few sections in the book, we learned how to parameterize 3D surfaces by taking cross sections. So we're going to do the same. This parameterization is describing some surface in 3D. I don't know what surface this is, but if I do cross sections, I can start trying to figure out what is happening. One thing I can do to start is what I did before. This tells me that x is u, y equals u. That tells me that the x and the y coordinates are always the same. And the z coordinate is u plus v. So I can try to figure out, for example, what is the intersection with the plane x equals 0, which is the yz plane. First, this intersection is going to tell me that x is 0, so that corresponds to u is 0, but that means that y is also 0. And then z, if u is 0, z is v, so v can be anything I want. So the only intersection with this plane, the intersection of my object with my plane is the line, the z-axis, because x is 0, y is 0, and z can be anything I want. Okay? So what happens if I intersect now my surface? So let's call the surface S. So this was the work with S intersect the x0 plane. So what happens if I intersect with y equals 0? then the same thing happens, because that tells me that y is 0, so v is, or u is 0, and that tells me that x is also 0, and z can be anything I want. So it turns out that with this plane, with when y is 0, it's this plane, I also get one line of intersection. And finally, if I try, okay, let me see what's happening with z equals 0, so with the xy plane. Now, what this tells me is that u plus v is 0, and u can be anything I want. So these are all the points u, and v is minus u. U minus u. Okay? What points are those? These are the points where, how can I say, these are the points where x is equal to y. So that is the line x equals y in the xy plane. Okay, so what I get is this intersection is this line here. And now you can see what is happening is that, yes, all the points are sort of x, x, and x plus something else. So I can get any z value as long as I am in the plane that is here. Okay, so that is what's being parametrized. That is the plane. Do you have an equation for that plane? This is just the plane x equals y in 3D and in 2D. This is in 2D, that's a line, but in 3D, x equals y gives you exactly that plane. Okay? So this parametrizes a plane that is diagonal in passing through the z-axis. So now let's do it the other way around. I want to find a parametric equation for a segment of a cylinder. Okay, so I want a cylinder. What cylinder is this? This is x and y satisfy x squared plus y squared equals 4. So that is radius 2, something like this, and up to 1. So if I also draw the top, this is a drum like this. Okay, but I am only parametrizing the surface of that cylinder. That's what I want. So do you have any ideas of how we can parametrize this, x, y, z, and then we'll put it together as our r of uv? How could we parametrize these? S. You pick t, so t and s could work. I'm going to keep calling them u and v, but your parameters can have any names you want. So what we are doing here, what Jacob was doing there, is first of all, just look at the cross-section with the xy plane. That is a circle, and we know how to parametrize a circle in that way, actually. I know how to parametrize it. This is a circle of radius 2. I know that these coordinates are r cosine theta. Just use cylindrical coordinates. That's what cylindrical coordinates do. They parametrize cylinders. So this is r cosine theta, r sine theta. That parametrizes that point, and by the way, this is parametrized with theta between 0 and 2 pi, parametrizes one full loop. And then for each one of those points in the xy plane, I want z coordinates anywhere between 0 and 1. So I can take this to be 2 cosine u, 2 sine u, and the z is going to be v. But now I have to specify where these live. With u is going to be the parameter that goes up to 2 pi, and v is up to 1. Okay? So what is happening here is that we have a restricted a restricted parameter space, u goes up to 2 pi, and v goes up to 1, and the parameter space is a rectangle, and then we are parametrizing the surface of a cylinder with that parameterization. Okay, so our parameterization goes from uv is sent to ruv, and the coordinates are what we wrote above: 2 cosine u, 2 sine u, v. There are many parameterizations, because again, we can parameterize these as sort of like different speeds in u and v directions, but this is just one of them that works just fine. Next, what we're going to do is use this parameterization to find the surface area of a cylinder, and so on. So here is just a better picture of the cylinder and the parameter space that corresponds to that parameterization. What's this parameterization doing? It's a cylinder in the y direction. So what I can do to figure that out is that call this x. So again, I can write x is 2 cosine u, y is v, and z is 2 sine u. And what you do to find, okay, this is hopefully some sort of algebraic expression for a surface. So you're trying to find relations between these variables, what we did before. In this example, we just found that x is 1, and then y and z can be anything. In this example, we figure out that x equals y, and that was the algebraic relation that basically describes every point that is parameterized like this. Here, we started from an algebraic relation, and we used that to come up with a parameterization. Here, I have some badly written coordinates. Let me redo 2 cosine u, 2 sine u. And you want to try to find some equations that are some algebraic expression that we recognize. And from this and this, you realize that x plus z squared is 2 cosine, so 4 cosine squared plus 4 sine squared, that is 4. So that tells me, what this tells me is that when y is 0, so in the x, y, z, so in the xz plane, my cross section is a circle of radius 2. Okay? 2 and 2. And then the y coordinate is equal to v. It can be anything. So I have a cylinder, which, by the way, it extends this one. It is, first of all, it is the surface of this cylinder, not the entire, it's not solid. And it extends infinitely because our parameter space, in this case, was all of R2, okay? And then that's parametrizing that infinite cylinder. We need an infinite amount of V to be able to parameterize the infinite cylinder, all the possible y coordinates. In U, as you go along in U, if you fix a V, what is happening? If you fix a V, what is this line in the cylinder? Suppose like here V is 1. It doesn't cut off, so I just drew it somewhat badly. Maybe I can draw. So what I said is this cylinder really doesn't stop. I don't know if maybe I can draw it like this just so you know that it continues. And similarly here, it just continues. But if y is fixed equal to 1, what that means is that I'm intersecting with y equals 1 and seeing what curve do I get in there. And that curve will be this circle. And as I move in u like that, what's happening is that I'm doing infinitely many loops around the cylinder. Okay? If I fix u and go like this, if I fix u, then what happens is that I'm fixing a position in the circle, and then I'm letting y run wild. So the purple line corresponds to a line, a straight line along the infinite direction of the cylinder. Okay? Those are going to be called grid curves, and we just use them to sort of like figure out paths on surfaces. Those are the simplest types of paths on surfaces. And as you put them all together, you see that if I consider all the possible grid curves like this, what I get is actually what I drew in my cylinder, essentially, which is I get, if I go in the fixing v direction, those are all these circles. If I fix a u, then what I get is these straight lines, and together they are basically the ruling of the surface. That all together, all those lines together, they actually define the surface. Okay. All right. So as I said, you can do parameterizations in a finite parameter space or an infinite parameter space, finite or infinite in area of the parameter space. And in this case, they are limiting what we can do with u up to pi over 2 and v up to 3, from 0 to 3. So what happens if I stop there up to pi over 2, up to pi over 2, and the xz plane, that is only from here up to here. So it's only a fourth of the cylinder. And when I go from 0 to 3 in v, I only advance in the y direction up to 3. 1, 2, 3. And in x and z, I just have this. So I have this figure. And notice that I'm only parametrizing a piece of the surface of this cylinder. So it is only this side that I'm parametrizing. And this one and that one are not really there. Okay? So it's just that sort of like, I don't know, some cover of some box or something. Okay? So you have to pay attention to the parameterizations, what the parameter space is, so that you actually get the right region. This, as you can see, this will come into play when we're trying to find the surface area, and we are going to set up some double integral. The double integral will have to do with this, sort of like, what region are we trying to parameterize? That will determine the bounds of our integrals. How about finding a parametric equation for an elliptic paraboloid? So this is just one example of infinitely many, where you can just take z to be a function and then parameterize the graph of a function. We know what a paraboloid looks like. So this is going to be, let's see, and z is 0, and so it's just going to be when if we fix 1, it's longer in x that is in y. So it looks like this. something like that is our paraboloid, and that is the graph of the function, so it is hollow, and I want to parametrize that paraboloid. In this case, the x and the y, they don't give me any region, so the x and the y are wild. They can just go anywhere, so I'm going to let u and v be just the entire R2, and this is going to parametrize this paraboloid by simply taking r of u and v, b, the coordinates, I'm going to put u and v here, and then the height, I know what the height is, u and v, and f of u and v in general. So in this case, is the parameterization is u, v, and then u squared plus 2v squared. So that is this parametrizes, and if you want to do it for any function of, for any graph of a function, you can always do u, v, f of u, v. That parametrizes the graph of a function. Okay? Okay. Now, parametric surfaces, so the surface of a graph of a function, is fairly simple. Those are fairly simple graphs, but parametric surfaces can be extremely complicated, and you can model very complicated things with just 2 parameters as you run through a parameter space. So this is one example of a surface that can be parametrized. I hope you can see. Can I do this? Oh, yes, I can. You can see the equations there of the x, the y, and the z coordinate, where u and v are just going between 0 and 1. But when you parametrize between 0 and 1 and you plot all the points, you get this, which is pretty neat. So there's an art to this, to how to figure out what is a graph and how to parametrize things like this. But you can play enough with functions until you start getting the hang of it. Okay, so now I think I need to go back to a height. Okay, so something that has helped already in trying to understand the parameterization are what I call grid curves on parametric surfaces. So if I have u and v, and through r of u, v, it's parametrizing some surface, like this, then usually the way I just drew my curve, those lines that I just drew to give a sense of what the curve looks like, or what the surface looks like, those are precisely these grid curves I was talking about. So you fix, so for a point, u0, v0, that will land over here. That's the point r of u0, v0 is somewhere in the surface. And then when you fix one of the coordinates, so fix, for example, u equals u0, then what you are going to get is, in parametric space, you get a line like this, and when you map that line, that is going to give you some curve that goes through that point, okay? And if you fix v0 and look at all the points that have that coordinate v, that is going to give you some other curve on the surface that goes through that point. And those are called the grid curves. And as you move u0 and v0, it gives you curves that are sort of like they they draw the graph for you as you would move. If you move all these purple lines, it would give you some sort of like scan of your surface by line, right? And similarly with the other ones. And we're going to use these to find tangent planes. To the surfaces, given a parametric surface, we're going to be able to find tangent planes because we're going to use these curves. We already know how to find the tangent vector to a parametric curve. Okay, so let me first actually give you RU is going to be the curve that you get if I let U run for a fixed V naught, okay? And RV is the curve that you get when you fix U naught and let V run. Now those are curves of one parameter, and we know how to find tangents. So we're going to be able to find the tangent line or the tangent vectors to exactly at that point. We're going to be able to find those tangent lines and tangent vectors by just taking derivatives with respect to u of RU and with respect to v of RV. And those together are going to give me a way to compute tangent planes at any point of our parametric surface. Then we're going to use that to compute integrals also. So as I said, these can be very complicated. So we have a parametric space here of u and v. The parametric space is really easy, but through this parameterization, you can parametrize that are u and v. It does parametrize these sort of like thick helix. And now we want to know what happens as I parametrize one of these grid curves. So let's fix v. Okay, so let v just fix it. And now I want to know what is R of u, but with a fixed v naught. For a fixed v naught, well, I can just simply plug in, and this is going to be 2 sine of v naught times cosine u, and then 2 plus sine of v naught sine of u, and then u plus cosine of v naught. How do I interpret this? V naught is a constant, then sine of v naught is also a constant. Okay, so just put 2 plus sine of v naught. That's some constant. Let's call it k. Okay, then what I have above is just k cosine u, k sine of u. By the way, k, the sign is between -1 and 1, so k is positive. Okay, we don't want circles of negative radius, right? So k is positive here. K cosine u, k sine u, and u plus cosine of v naught is some other constant. So let's call it, what's another good name for a constant? Just see. Okay. And now you see what this is parametrizing is in the xy plane. This is a circle of radius k. And this, as u moves, the constant, as u changes, this is just going to increase with u and decrease with u. So if you try to draw what is happening, it's going to start somewhere here, and then it's going to start going in circles and going up. So this, what it does, is just follow the spiral at some point. So you can see that with v constant, the grid curves are the spirals on the surface of the helix. Okay? I'm not going to do the one with u constant because u constant is a lot more complicated. What it's doing when u is constant is actually doing a double helix in that it's going around, but also moving about as it goes up. So it is doing sort of like this double work of going in a circle in the XY plane, and it's also going in a circle, sort of like a circle that is rotating about the x-axis, about the z-axis. So it's a very complicated motion, but it's just cool to see that you can parameterize some very special curves that define this surface. Okay, so now what else? Let's, well, parametrizing planes is important. So let's try to parameterize or give an equation for a plane that passes through a point and it's and it contains two vectors. So how would I do that? There are a couple ways that I could do this. So I want a plane that passes through a point, P, and it contains two vectors, so a vector A and a vector B. Okay, I'm going to give myself names for all of these things. P is going to be x naught, y naught, z naught. A is going to be A1, A2, A3, and B is going to be B1, B2, B3. So these two lines, they do determine a plane like that, and if they are starting from P, then that is going to determine a plane. Okay? But the easiest way of doing this is to actually carry this out at 0, 0. Okay? Put A and B here. Find this plane first over here, and then add the coordinates of P to the whole thing, because that will carry the entire plane to where you want it to be. Okay? So this plane over here is actually simple to parameterize. If you want to parameterize a plane that contains those two vectors, then, well, I need to contain every point that is a multiple of A. So it has to be U times the vector A. Let's put little arrows to know those are vectors, plus V times any copy of B. And then A plus B, that's another point that is on that plane. So that parameterizes this one. And to parameterize that one, you just do the same thing. But now I want to add the point P. So you put the point P, and then U parameter times A plus V parameter times the vector B. That gives you a plane in coordinates. Let me, if you want, I can give you the entire coordinate system here. This is x naught plus SA1 plus, not S, U, plus V B1, Y naught plus UA2 plus VB2, and Z naught plus UA3 plus VB3. That is a parameterization of the x, y, z coordinates of your plane with two parameters, u and v. Okay? The other way of doing this is that if I had a point P and vectors A and B, what I can do is find A cross B, the cross product, and then use, so if A cross B is, say, C1, C2, C3, then I can use the normal vector and point equation of a plane that is going to give me C1 times x minus x naught plus C2 y minus y naught plus C3 z minus z naught equals 0. that is also either this one or this one are two ways to compute the equation of a plane with a given two directions and two directions on a point. If you want a parameterization, then this is a parameterization. This is the equation of the actual plane. There's no parameterization happening here as it is. Any questions on how to find planes? What about a parametric equation of a sphere centered at the origin and radius r? What do you think? What should we use here to parametrize? I want a full sphere parametrized, but just the surface of the sphere. Spherical coordinates, yes. So remember, I can parametrize any point in R3 using spherical coordinates, but the spherical coordinates are particularly well suited for things with symmetries about the origin, specifically spheres. So what is, first of all, if I parameterize this we know how to do. If I parameterize this with spherical coordinates, let's actually be gone before I put x, y, and z. What are the spherical coordinates? So I have rho, I have theta, and I have phi. There's going to be bounds. So let's just start with rho, theta, and phi. What are the parameters here to describe a sphere of radius r? For rho. Rho, remember, is the distance from the origin to any point on the sphere. So that would be a full sphere, but I want to just the surface. Right? So if I want to parameterize an entire sphere, then the rho would be go all the way from 0 to r. But here, we are just parameterizing the sphere, so the rho is fixed equal to r. Then theta, I can go all around in this direction. So theta is going from 0 to 2 pi. And then the phi, we are parameterizing the entire sphere. And remember that phi goes from here all the way to here. We want the entire sphere, so this is going to be going all the way to pi. And with these parameters, the coordinates for x, y, and z are r sine phi cosine theta, r sine phi sine theta, and r cosine phi. That r would have been rho, except that rho is fixed equal to r. And now you can see that these parameters, x, y, and z, these coordinates, only depend on two parameters. So we do have a parameterization. I'm going to call it u and v, but this is theta in this guise, and v is going to be phi in this guise. If you want to call your variables theta and phi, that's fine. But I just want to put it like we did for every other one. And now u is going up to 2 pi. And v is going up to pi. So it is this parameter space. And this parameter space is going to parameterize for me an entire sphere of radius r. Okay? So that parameterizes the entire sphere. Notice that there is no r in the parameter space. It is the parameterization itself that takes care of the r by fixing that r in the parameterization. Okay, so the parameterization depends on r, but r itself is not a parameter. Rho is not a parameter, rho is fixed. So there is the same Like they took theta and phi sort of in a different order, but it's the same parameterization. Okay? Okay. Now, there's another type of surfaces that are really useful to know how to parametrize, which is surfaces of revolution. So what we're going to do is we start with a graph of a function between some a and b. You start with a graph like this, and then do a revolution about the x-axis, and that's going to give me an object like so. Okay, so I want to be able to parametrize these objects, and what are the coordinates of these things? Well, in the xy plane, it's clear that the coordinates here are x, f of x, but then I want to rotate that in the yz plane, right? So the rotation, to be able to rotate, what I'm doing is a circle in the yz plane of radius f of x. Okay, so in any of these cutoffs, so fix a point here, cut it off, is going to be a circle, and that plane, in that plane, is sort of like in the y and z plane, I have this much length. I want to parametrize a circle like this, and a circle like this is parameterized by f of x cosine theta, f of x sine theta. Okay, so overall, in the entire parameterization, what you get is that R of, let's say, uv is going to be u f of u cosine of v f of u cosine of v. That is a parameterization in uv space of this. If I put no limits on this, then I'm going to get sort of like an infinite object of revolution, which could be something like Gabriel's horn or something. Sometimes we do that, but typically in here, the parameter space u will be between something and something, and the v, which corresponds to the theta. To get a full revolution, you go from 0 to 2 pi, but if you're only doing like a quarter of, then you would go from 0 to pi over 2 or some other range if you were going to do something different. Okay, so those are the surfaces of revolution. And so let's try to find the parametric equation for the surface that happens when I do this. So what do I get for x between 0 and 2 pi? So the object is going to follow the graph of sine of x. Sine of x starts at the origin, so it goes like this in a full loop up to 2 pi, does this, and then rotate it, and what I'm going to get is an object like this, like two footballs back to back, or two coconuts somehow. Okay, so I want to parameterize this thing, so I do like I did before. R of uv is going to be u f of x, so sine of x, sine of u cosine of v, sine of u, sine of v, with u between 0 and 2 pi, and the v, which is sort of like the theta, also between 0 and 2 pi. So this equation parametrizes that object. There it is, a better drawing of the two footballs. Okay. So as I said, we can compute tangent planes using this. So what we're doing to compute tangent planes is we fix a point and then we look at those two grid curves. There's a grid curve, there's a grid curve, and those are going to give me two tangent directions. And now I know how to parametrize the equation of a tangent of a plane with two directions at a point. So now I can figure this all out. The direction RU is the derivative will be given by a shape like this. So you take x partial with respect to u and then evaluate at the point. And the direction in v is given by this these set of partial derivatives. Those are the derivatives of the grid curves in the direction of u, the grid curve in the direction of v, and then taking tangent lines. So we can compute what the tangent plane is going to be. First of all, by the way, if RU and RV, if the cross product is not zero, that means they're not parallel, and therefore there is a well-defined perpendicular direction. And in that case, we call the surface smooth at that point. In colloquial terms, it just has no corners. And then the tangent plane will be a vector or a plane that passes through the point P, and it has tangent vectors RU and RV, or that the normal vector is the cross product of RU with RV. So let me give you an example of how to figure out a tangent plane. So the parametric equation is just given by u squared, v squared. It's u squared, v squared, u plus 2v. So we want to figure out what's happening at the point 1, 1, 3. So we're going to figure out, first of all, I actually need to figure out what parameter u and v corresponds to that point. What parameters actually land on the point 1, 1, 3. So what are those? They have to satisfy that u squared is 1, v squared is 1, and u plus 2v is 3. That is that u can be plus or minus 1, v can be plus or minus 1, and u plus 2v has to be 3. So that all in all tells you that the pair we're looking for is the point 1, 1 in parametric space. Okay. And now I compute partial derivatives. So the partial with respect to u is 2u, 0, 1. The partial with respect to v is 0, 2v, 2. Evaluate at the point. So what is RU at 1, 1 and RV at 1, 1? That is 2, 0, 1. And this is 2, 0, 2, 2. Okay. So now to find the plane, I'm going to actually do the cross product just to see if it is even smooth at that point. So I'm going to find the cross product of RU and RV. And remember that that is given by a determinant like so. And the result of this is the vector minus 2, 4, 4. Which is, I just need that direction. So if you see that is the multiple of another easier vector, then I can take my normal vector to be minus 1, 2, 2. And now that I have a normal vector and I have a point, I know how to compute the equation of the tangent plane, because so we found that I have a point 1, 1, 3. I have a normal vector minus 1, 2, 2. So the plane will be given by minus 1 times x minus 1 plus 2 times y minus 1 plus 2 times, well, what is that? Z minus 3 equals 0. That's the equation of a plane that passes through a point with perpendicular vector n. So this is the equation of the plane, of the tangent plane we were looking for. This simplifies a lot. This is the plane x plus 2y minus 2z equal minus 3. No, it would not have mattered in the equation of the plane. If you use minus 2 for 4, everything would be multiplied by 2. And maybe you would have noticed then in this equation that everything is a multiple of 2 in the coefficients, and I can divide by 2.